Hello, dear students. I am Dr. Shaila Apte. I am generating these videos for signals and systems in order to explain very basic details of it or conceptual for better conceptual understanding. I have published a book called as Signals and Systems by Cambridge University Press. This is available on Amazon or any other site you can go and see. So let us start with understanding of the basic concepts. So if we consider the signals, what are the signals? Speech is a signal, image is a signal, video is a signal, earthquake is a signal, right? ECG is a signal. All these are naturally occurring signals and naturally we would like to process it. Now when we want to process it, it is existing in the analog form. Analog form means it is continuous time, continuous amplitude signal. So continuous time means how many time instance we will have to capture? Infinite. How many amplitude values we have to capture? These will also be infinite. Then it is just impossible to interface it to our digital computer, isn't it? So what we should do? We should take few samples of the signal and then see whether we can process it or recover it at the receiver and also faithfully so that there is no loss. So we sample the signal and convert it to discrete time continuous amplitude signal. Amplitude remains continuous, but we convert it to discrete time by sampling. And then to convert the amplitude axis also to discrete values, we convert it in the digital form where the amplitude axis is also digitized, time axis is also digitized, so it is discrete time, discrete amplitude signal. Are you getting it? So, as I said, we'll have to first sample the signal. Now, when we sample it, there must be some rules for sampling. Because when I sample the signal and say transmit it from one end to the other, at the other end, these samples should be utilized for recovering the original signal in the analog form. Otherwise, what is the use if there is some loss occurring? So there should be no loss, and we should be in a position to faithfully recover the signal at the receiver end. So there are some rules for sampling. The rules for the sampling say that if you want to sample the signal, find out what is the bandwidth of the signal first. If say bandwidth of the signal is W, let us say it is 1 kilohertz, then what should be the sampling rate? The sampling rate should be greater than or equal to twice W. So if my W is 1 kilohertz, I'll have to sample at least at 2 kilohertz. So I will have at least 2 samples per my cycle of the signal. Considering that it is means periodic, of course, but it can be aperiodic also, and still we should be in a position to recover it. It may be quasi-periodic. Now, when I am sampling, I am expecting that there is also no aliasing possible. Aliasing means high frequencies are aliased or misinterpreted as low frequencies. That is called as aliasing. So we'll see it shortly what is aliasing. And after that we do digitization. Now how digitization is possible? This is a quite wonderful thing. You know, we have wonderful properties given to our human ear, and this is a God's gift. God has given the sensitivity to the human ear such that very small changes in the amplitude are not detected or not understood by the human ear. So we take the advantage of it. We have discovered, human has discovered, no doubt. But how this discovery was possible? Because of the God's gift. So we digitize it, we represent it in the digital form, that is ones and zeros. So suppose we consider the 1 volt signal digitized to only 4 bits, we represent it as 1111. But how much it comes to? It comes to 0.5 plus 0.25 plus 0.125 plus 0.0625. It comes to 0.939375. Now, if I want to represent 0.94, I will represent it by the same value. So, even though there is some small change in the amplitude, it is not captured in the digital form. But still, no problem. Human ear is not in a position to distinguish that. So, because of this God's gift, we are in a position to enter the digital world, and that is amazing, isn't it? So, let us try to understand the sampling of the signal. Now, here is some sine wave that is plotted, and its frequency is 10 hertz. So, if I want to represent it, if I want to sample it, I understand that if I have some 10 samples from the 10 hertz one cycle, then I can recover it properly. Okay. So here I have shown that there are 10 samples taken from one cycle of 10 hertz signal, and then you can see the shape of the sine wave, and this shape of the sine wave is it is visible from these samples. Is that right? So I can recover the signal perfectly. Now, whenever it is a multiplication, see in the I will go to the earlier point. Uh, in the earlier slide, you have seen that we have done multiplication of the signal with the train of samples. Now, in time domain, when there is multiplication, in the transform domain, it becomes convolution. So, what is the transform of the 10 hertz signal? It is just 10 hertz frequency shown at plus 10 hertz and minus 10 hertz. I will talk about this minus 10 hertz also later. So this is the transform for the 10 hertz signal. What is the transform for 100 hertz sampling frequency? It is also existing at 100 hertz. Now we do convolution. When we do convolution, you will find that there is a repetitive pattern of 10 hertz minus 10 hertz appearing around 100 hertz also. So it is 110 hertz, 90 hertz. Here it is minus 110 hertz, minus 90 hertz, and it is existing all over the entire time axis. This is the repetitive pattern. But there is isolation in the spectrum. The spectrum between minus 10 hertz to plus 10 hertz can be isolated from this repetitive pattern. So if I isolate it, if I just pass it via a window and I isolate it, the isolated signal spectrum just has 10 hertz and minus 10 hertz. Now you can recover. Now what you do is, you take the signal samples and generate a sinc function around it. And after generating a sinc function around every recovered sample, then you interpolate it and generate it using the dots, and you generate perfectly the sine wave that was transmitted from the transmitter end. This is because we have obeyed Nyquist theorem. We have sampled at a sampling frequency which is greater than or equal to W, sorry. Now suppose what we do is we sample it at below the Nyquist rate. So if the signal is of say 90 hertz, what is the Nyquist rate? It should be 180 hertz. But let us say I sample it at 100 hertz. If I sample at 100 hertz, then what will happen? For these 9 cycles of the signal, I will have 10 samples. So for one complete cycle of the signal, I will rarely get only one sample. Now, is it possible to recover it? The answer is no. Because in this case, what is happening is, because the signal has W, that is the bandwidth equal to 90 hertz, I have sampled at 100 hertz. So I can represent the frequencies only up to 50 hertz. and this 90 hertz will be folded back and I will be reading it as 10 hertz. Just look at this. Here I can represent only up to phase by 2, that is 50 hertz. Sorry. If the signal has frequency of 90 hertz, it folds back and it is represented at just 10 hertz. This is what we call it as aliasing. Now I'll tell you about something about the negative